Okay, hi everybody. We have the pleasure to have Mohammed today, which is in third year in PhD in LVA. Between I think the lab and probably no.
The lab.
Anyway, yeah. So yeah, you have like between 30 and 45 minutes.
Okay.
Thank you very much.
Did you notice? I will talk today about my thesis work. I'm developing a method called the Maximally-Coherent Reference technique. And I apply this method to the source extraction problem and also to the resynchronization of sequential measurements. The work is under the supervision of Professor Jerome Anthony and Dr. Quentin Claire. Okay. So first, to introduce the problem. The problem is about having a system that contains several incoherent sources. These sources could interact in the frequency and or the space domains, and also probably the contribution of these sources are submerged in a considerable amount of noise. All these conditions result in a smeared, if you can say, a smeared reconstructed field, where it's hard to identify separate sources. There is an equivalent problem in the case of sequential measurements. Even if the sources are well separated in frequency and space, the loss of the phase between these sequential measurements produce the same smeared reconstructed field. A solution for these two equivalent problems is the reference techniques, which I'm dealing with in my PhD principally. It's called also the coherence techniques. It was introduced in the 70s of the previous century, in this technique they use some fixed sensors. They call them the reference sensors, like this. So we have the array, and we have some fixed sensors. They don't move in space. They could be also accelerometers, so they could be a different type. And they use the information from these references to extract the coherent spectra, and I mean by the coherent spectra are the signals produced by the sources of interest on the microphone array, and not by the noise or any other source not of interest. To understand how the reference technique works, let's introduce the mathematical formulation of the problem, where we have a system H and a matrix of sources S, which go through the system and contribute with a matrix of contributions X, which we try to measure. But when we measure, actually, we don't measure X, we measure Y, because there is always some additive noise. And we aim to, in the source extraction problem, or the source equation problem, we aim to extract or estimate this X as close as possible. So we want to get X hat as close as possible to X. The coherence technique uses some other set of sensors. They call them the references, R, the matrix R, which is nothing but a linear combinations of these sources. It's supposed to be more clear than Y, or close to some sources that I know, and they also may be contaminated with some noise. Okay, and then the solution is obtained through reducing the rank of Y, restricting the rank of the cross-spectral matrix of Y to that of R, okay? Through a least square estimation or a least square solution, which is defined in this equation. Okay, so I try to get G, the operator G, and this is the least square solution, where SYR is the cross-spectral matrix between Y and R, and SRR is the cross-spectral matrix between the differences. Okay, and we can see that there is an inversion here, which will introduce most of the problems that's encountered during implementing this kind of techniques. Okay. Principally, this technique is based on very strong assumptions. I call them the perfect references assumptions, where we use R number of references strictly equal to the number of sources, if I know them. Sometimes, most of the time, I don't know the true number of sources. And these reference signals are uncorrelated between each other, among each other. Okay. In this case, the cross-spectral matrix SRR will be well-conditioned, and there will be no problem in this inversion. Okay. But in the realistic case, which is problematic because the user usually don't know the true number of sources, so he or she tend to use a higher number of references. So we will have usually R more than S, higher than S, and in this case, they are correlated by definition. And hence, the cross-spectral matrix SRR will be badly conditioned, or maybe singular if we have a very large number of R, the references. And this inversion will be problematic. Okay, the solutions in the literature, generally, we can call them a rank reduction technique, which are based on reducing the rank of the cross-spectral matrix of the references, SRR, to the number of sources. So there is also some sub-problem implied in this problem, which we need to know the number of sources at the beginning, or estimate them. And then to restrict the rank of the cross-spectral matrix of the references to this number. A first attempt was through the partial coherence technique, or it's called also conditional spectral analysis technique. I will go directly to the limitations, it's very famous. The first limitation, it requires some ordering operation between the signals of the references, based on causality or something. And this problem that there is no robust criteria, there is no robust criterion on which we can base this ordering operation. And hence, we can end up with R factorial number of models that we want to analyze them. The second problem is when the user uses very large number of the references, and in this case, I mean larger than the number of sources. This may lead to singularity. So it will stop to give error. The second solution is called the virtual coherence technique. And the virtual coherence technique is nothing but a principal component analysis of the reference set, which is a truncated SVD. They do SVD of the cross-spectral matrix of the references, and then by estimating the number of sources, which is another problem, they truncate the eigenvalues or the singular values to that number of sources they have estimated. And the limitation of this technique, we can say that this technique has a mathematical limitation that it doesn't work only if the noise on the references, we have the references, and we have noise on them also. If these noises on the reference sensors are correlated, okay, or even the variance of the noises on the references are different, then the truncated SVD or the SVD fails. And in this case, the first S singular values, where S is the number of sources, do not represent the field of interest. Okay. So if we don't have a covariance matrix of noise on the references that is proportional to identity, which I call it scalar noise, I can't use truncated SVD anymore. Okay. There is another problem that is very interesting because it's never discussed up to my knowledge in the literature, which is the problem of a well-conditioned reference cross-spectral matrix. The previous problem, which is the traditional one, everybody is talking about it, is the badly conditioned spectral matrix, which will produce some problematic inversion. But what if we have a well-conditioned cross-spectral matrix, but due to noise, high level of noise on the references, that made this badly conditioned cross-spectral matrix well-conditioned? And in this case, if we made SVD, principal component analysis, this is, for example, data from electrical motor from Siemens, where there is here a microphone array of 15 microphones, and here is some references they use to do source extraction, and we can see here that even year over year, there is, you can't put a threshold between important eigenvalues and noise. They are gradually, the principal components are gradually decreasing. There is no clear threshold to set, and then you can't apply truncated SVD. So this is also another problem. The proposed solution, which we call it the maximally-coherent reference techniques, is simply we simply try to get a reference set that is essentially nothing but a linear combination of the measured ones, so as to this reference set are maximally correlated to the array data, okay? Because the array data is coming principally from the sources, and also the references are coming from the sources. So we try to get linear combinations of this R matrix, the reference matrix, so as to the new reference set are maximally correlated to the data that I want to denoise. Okay, and this technique can be done iteratively, one by one. We get B1, so as to this B1 makes this Z1 maximally correlated to 1, which is the data in the array. And then we decorrelate this one, decorrelate Z1 from the data, and then we repeat. Okay, we repeat until a number S of Z1, a number S of Z. Okay, from Z1 to Zs, where S is the number of sources. We always need to estimate the true number of sources in the system. Okay, and we derived that this solution can be done in one operation, which is this generalized eigenvalue problem. So there is no need to the recursive algorithm. Okay, so we can see from all what I have spoken that either truncated SVD or our method needs to estimate the number of sources, okay, which is a main sub-problem. And how to infer about it? Using the data, the microphone data we have, we can infer how much these data are coming from, how much incoherent sources. There are several techniques. We tried to apply a direct likelihood ratio test, which is based on mixed theorem, which is asymptotic. And the first problem we faced that this theory, mixed theorem, are only formalized for real data. So we reformalize it for the case of complex data, because we usually deal with complex data coming from Fourier transform. And then we discovered that there is some limitation due to mathematical limitation to the mixed theorem when it comes to factor analysis models. Our model is a factor analysis model, so sometimes it fails. The Wick's theorem, the traditional one, fails. The traditional Wick's theorem are based on comparing each two successive models. I compare a model with only one source to a model with two sources, and then if a model with two sources won, so I compare a model with two sources to a model with three sources, etc. to the end, to the complete number of references I'm using. So when we found that failing to some mathematical reason, we found out that if we compared each model model with one source, model with two sources, etc. separately, comparing them to the saturated model, which means the model of the whole set of references, this will be more robust. And then we tried this. So we have now two asymptotic tests. And then we tried to fix the likelihood ratio test using bootstrapping techniques. So we did bootstrapping to fix this, and it worked very good. And finally, but it takes some time, it's a time consuming, bootstrap is time consuming. And then we tried to split the data in two parts, and we tried to cross-validate, to do what's called a cross-validation. Okay? For example, if you plotted some error in the data or some property, and you find it some metric, and you find it by increasing the number of sources in your model, the error decreases, it will come to some value, and then it will increase again. This value will correspond to the true number of sources. This is simple. Okay, actually the estimation of the number of sources is a huge amount of work. I can introduce it in another presentation, but I will give a small idea about it. For example, in this simulation, I'm simulating 4 sources. I'm varying here the number of microphones on the array, just to test the robustness. So the number of true sources are 4. And here the number of estimated sources based on the traditional mix theory, which is by comparing each two successive models. Okay? And this is by comparing to the each model to the saturated model. You can see the robustness. I think it's clear from this simulation. Yeah, and for searching more why is this, we made another simulation where we repeated the simulation many times, and we draw the histogram of the likelihood ratio in the 2 tests, in the 2 cases, the traditional one and the saturated test. Okay, and this is the asymptotic distribution that should follow. Okay, which is a function of chi-square distribution of some parameter. Okay, and we can see. Here we used for 1,000 snapshots, and here 10,000 snapshots. So we're trying to see how it looks when it converts. And we can see that the asymptotic distribution that is theoretically should follow is going ahead to the right, which will overestimate, which will lead to overestimation of the number of sources. And here is the same, even after 10 kilo, after using 10 kilo snapshots, it is the same problem. But here, you can see that after convergence, the histogram and the distribution are quite coincident.
On the slides, can you use the cursor on your screen so that the
yeah, for sure.
Just the maps. Yeah.
Okay. To see the difference between the performance of the least squares solution, the truncated SVD solution, and our solution, we did this simple simulations where we simulated 3 sources. All the signals are simulated as random Gaussian, complex Gaussian, and we simulated 20 references and 100 array microphones. And we are plotting here is the error between the estimated x and the true x, simulated x. Okay, this error defines this equation. And we are repeating the experiment with different signal to noise ratios of the references. So sometimes we have clear references, and sometimes here we have clear references, and we have here very noisy ones. Okay. As you can see, when the references are very clear, and they are of larger numbers than the sources, we can see 20 references and only 3 sources. So the truncated SVD, the least square solution here in red, it overestimates. It gives very high error. This is very high error due to the bad condition of the cross-spectral matrix of the references. Okay. Truncated SVD solved this problem. As so our method solved this problem. Okay. And when the references are very noisy, the 3 techniques more or less behave the same. If we introduced a 90% correlation between the reference, the noise on the references, in this case, the truncated SVD failed, clearly failed. You can see here, especially when you increase the noise on the references. So we have high noise and correlated noise. So the truncated SVD is no more working as we anticipated. Here we did a sensitivity study. We simulated 15 microphones with a scalar noise on the references, which means truncated SVD should give reasonable results in this case. In this direction, we are reducing the SNR of the references. So SNR of the references here equals 20, equals 0, equals minus 20 dB. And here we are increasing the number of references, the number of sensors. Okay, so in this directions, I should making problems to the truncated SVD. And in this directions, I should be making a problem in the face of the least square solution, because I'm increasing the number of references. Okay, and I'm plotting here the estimated SNR of the array, or of the output of one sensor for sure. Again, is the estimated one. So the truth here is this diagonal. And I have the 3 solutions here. Okay? The truncated SVD in red, and the least square solution in purple, and our solution in blue, in dotted blue. And we can see that when we have a very nice references of 20 dB signal to noise ratio, nearly all the methods works well. Okay, but when the number of references are very large, like 25, you can see that here the least square solution gives some overestimation in this way. See this overestimation. Okay. Truncated SVD for sure, when the signal to noise ratio of the references are low, truncated SVD gives the worst results. Okay. Let's introduce a correlation between the references, the noise on the references. So now the noises of references are correlated, which, as I said before, will introduce a problem in the face of truncated SVD. And this is apparent if we compare the column in the middle here. Truncated SVD is in red. The other 2 solutions are very good. They are on the diagonal. Okay. If we came back to the scalar noise case, truncated SVD is with them. Okay. If we convert, for example, this graph, we can't see the solution of the truncated SVD at all. While in the scalar noise case, at least we can see it with the others. Okay? So it's clear now that introducing a correlation between the noise of the references is very problematic to the truncated SVD. We did another simulation. In this simulation, I tried to visualize the simulation and make it give it a little bit of a special dimension. So here I simulated x. I think this should be x, not x hat. This is the simulated coherent spectra coming from one source in the middle of this array. This is the array, the complex spectra, and this is the amplitude, this is the phase, and this is the real and imaginary parts. Okay, I added some noise, and if we compare, we can see that the noise destroyed both the amplitude, the magnitude, and also destroyed the phase. Okay, this is my solution, the maximally correlated reference solution. It retrieved very well the magnitude, and also it retrieved the phase, and for sure the other parts. Okay, and truncated SVD underestimated the amplitude. There is a great underestimation produced by the truncated SVD solution, and also failed to retrieve the phase. The least squares estimated an amplitude that is closer to y than x, which is by definition. Because least squares, by definition, try to get the solution as close as possible to y. And also the phase, it failed to retrieve the phase. So it's clear the supremacy of our technique compared to the others. Moving from the simulations to the experiment, we did one experiment at the basement of LVA, where we used one shaker as source, fed by a Gaussian noise. And we used a total of 5. I'm sure the shaker is attached to a plate. This is in the coupled room. So in the coupled room, we have a plate in between. We have a shaker attached to the plate. We have 2 accelerometers as references, and also 3 microphones. And on the other side, we have the microphone array that we want to estimate the coherent part on it. So this is some pictures of the setup. And this is the results of the analysis of the data. First, this is the eigenspectra, which is the SVD, from the array and from the reference set. Okay, I just said that we have only one source. If you look to the reference, the eigenspectra of the reference signals here, you see like it's more 2 sources, not 1 source. Okay, let's come to our solution, which are the maximally coherent principal spectra, if you can call them. Our solution showing only one source separated from the ground noise. So it's even by visual inspection here, using this graph, you can say that we have only one source. Okay, but you can't say anything about this. And applying one of the source estimation techniques that we developed. For example, here I'm used the bootstrapping of the saturated likelihood ratio test. And you can see here also it returned one source in the majority of the frequency line, except from some frequencies. And I think they are due to the acquisition system. It was inside the room. And I made some other experiments, but with shakers, but with speakers, not with shakers. And I got, in these experiments, I got the acquisition system out of the room. And in this case, it gave very constant results. Okay. To test the ability of our technique to resynchronize successive measurements, I made a small game, if we can say. I took the signals of the array and divided them in 2 sets. And then I distorted the phase between these 2 sets by shifting the signals in the time domain. So I take the data from the array, I made them in 2 sets. I shifted shifted them in time, so there is no the phase is distorted between the 2 sets. And in this manner, I created the successive measurement scenario without the need for physically moving the array. Okay? And here we can look again at the results. Here is the measurement. This is our measurement. Okay? Again, this is the magnitude, this is the phase, the real part, and the measured part. Here is the phase distorted measurements. So this is the measurements after phase distortion between the two sets. The amplitude is clearly destroyed. Also the phase, this doesn't look like this. Okay, and for sure the other parts. This is our solution here. You can compare by vision here, this to this. And also you can compare the phase. The phase is well, you can say it was well retrieved. Yeah. If you looked at the truncated SVD, yeah, it retrieved the amplitude quite well, but it couldn't, the phase is still smeared. Okay, so compare this with this, they doesn't look alike. They don't look alike. And also the least square solution didn't succeed in retrieving the phase. Okay. Let me show another snapshot. This is another snapshot. By the way, all you are seeing now is at single frequency at a single snapshot. Okay, and this is the Fourier spectrum. If we look here from the phase, the original phase, and the distorted phase, there is no much distortion in the phase in this snapshot, but the amplitude is quite altered. Okay, here is our solution here in the third row. We can see this is how it retrieved the amplitude quite well, while truncated SVD, again, as happened in the simulation, it underestimated the amplitude. Okay? I'm not discussing the phase because they are more or less the same as the original one. Okay? And the least square also returned good results. Okay? Final experiment, which is coming from real data from the electric motor measured in Siemens, where we have a microphone array here. We're moving this microphone array, but I only analyzed one position. They used 11 sensors as references. They used 5 microphones and 6 acceleration tracks. And they had, for each position, they have 50 microphones. And for sure in this case, I don't know the number of sources. In the previous cases, either in the simulation case or in the experiment case, I know the number of sources. But in this case, the number of sources is unknown. Okay? If you remember from the early slides, these eigenvalues, that is hard to put a threshold through them because they are gradually decreasing. They are coming from these data. Okay, and here our technique said something about the number of sources because we have they used in their measurement 11 references, and here we estimated number of sources that is oscillating between 6 to 9 to 10. So we could say something about the number of sources. The number of sources for sure is not 11. And here I made the game again. I made the same game again. I took the array measurement, I split them like this. You can see from the real part here, like this. And then resynchronized them using our technique. I should have, I put the ground truth above. Here's the ground truth. The ground truth in the third row, which is not a good choice. We have here the magnitude again, and this is the phase. you can see, I don't know if you can see, there is here the fan part of the motor behind in the photo. And here is the real and the imaginary part. When I took this third row and I distorted the phase between two sets of microphones, you can see the phase distortion for sure here in this figure, in this picture, and also here. You can see here, I exactly split here to two sets. So you can see how the phase got distorted. And this is, in the middle, the retrieved phase using our method. The phase is comparing the second and third row. The phase is greatly restored. I didn't show the results for the other two methods because they were more or less the same on this data set, so there is no meaning of showing it. But at least our method got validated on realistic data. Okay, in conclusion, we can say that all the challenges that appear while solving the two equivalent problems of source separation or resynchronization of successive measurements, all the challenges that could appear actually is associated somehow to the condition of the cross-spectral matrix of the references. If it is bad conditioned, if it is badly conditioned, it will give some sort of problems, okay? And if it is well conditioned, it will give another sort of problems regarding this threshold and stuff. And hence, we proposed a novel solution to deal with all the reference-related problems at once. Okay? And these references may contain noises with different SNRs or different powers, which means in reality they are coming from different type of sensors. And also these references would, these noises on the references may be correlated. And we also introduced several techniques to select the number of sources. Thank you very much. I didn't take too much of time.
Thanks, Mohammed. Do you guys have any questions? Online?
Was it clear? A bit,
Pretty rough at the beginning.
yeah.
I didn't get in the end. Did you manage to find the number of sources in your CMS dataset?
To find what?
The number of sources.
Yeah, here I estimated the number of sources, but from what I get of information, there is no. There is no, how to say, there is no other people that made some analysis that I can compare with them.
Yeah, sure.
If I found, I could compare.
The truth.
Yeah, the ground truth here is.
Yeah, sure.
That's why actually I had to make experiments, because in realistic data you can't say anything about the.
Yeah.
Especially about when it's the case of these new machines of electric motors and stuff. Because at least in combustion engines we had some ideas from many years of research about the phenomena, the different physical phenomena that produces a sound, like the combustion noise and the mechanical noise, and the two types of mechanical noises. Good research on this.
I have another question. I mean, sometimes you can get sources that are really extended. I mean, for example, on motor, sometimes the sources can be large. I don't know how to say that.
Mm-hmm.
Do you cut those sources, or I don't know how to say that.
You want to say a diffuse
Yeah.
source feed?
Yeah. So, yeah.
Okay.
My mind is not really clear, but
If it is a mode of source distribution,
yeah.
okay, then separated sources,
Mm.
I think at least the method can extract the contribution of the sources from the noise.
Okay.
Okay. If given that the number of sources here are correctly estimated. Okay. So the source extraction problem, from my point of view, relies very much on the accuracy of estimation of the number of sources. That's why actually I'd like to give another presentation more dedicated to the techniques that we presented for tackling the problem of estimating the number of sources. Because they can't be put in the same presentation as the technique itself.
So in order to go a bit forward on Nicolas' question, do you have any insights on whether the source is large or not, or how do you know that it's 8 sources, though it's like
large in space? You mean like?
Yeah.
I think actually the reference technique or the coherence techniques originally introduced to solve the resynchronization problem, as I introduced earlier here. For example, if you have a big machine, maybe bigger than a motor, and you can't cover it with one array, or you don't have the cost of producing a special array for this mission, so you can use a prototype array and to move it. Okay, and what is lost here when you move this array actually is the phase. Okay, and the phase. There is I can say that if we assumed a constant level sources, so we can assume a constant level contributions from these sources, and what it changes with time is the noise term. Okay, so when you were in this position and you move to this position, the noise term here is not the same as the noise term here when you was measuring there. Is it clear? The noise term changed. And that's why in the resynchronization problem, we want to retrieve this, which is why. Okay? In the source extraction problem, not the resynchronization problem, which is equivalent, we want to extract this. So we want to get something like this. So they are the same problem, more or less. It's clear? So when we move the array, now we have a term n dash, that is not n. It changed. So the two problems are the same, more or less. Okay? And I don't think if we have, I really don't know what Nicola meant by diffuse source field, because maybe diffuse source field is actually due to this smearing that I talked about, because we like something like this. In this illustrative example here, this is not mine, I took it from an earlier paper of the lab. You can see here, this is a combustion engine, and this is the measured spectra where we can't identify anything, you can say. By using source separation techniques, we could have separate this mess into two meaningful results. One of them comes from this area, which is found by superimposing to the space. We found it, or they found it in their paper, due to combustion. It is the combustion area. So we could have said something. And on the other side, this a little bit distributed lighter noise is coming from the mechanical phenomenon. Okay, so we could have break down the overall diffuse field, I think you were talking about something like this, into two meaningful results that we can give a physical significance to them.
In one, the way I understood Nicolas' question would be, would you find 2 sources here, or 3 or 4? Because the one on the right hand side is quite spread.
Yeah, okay. If we came back to the literature of the noise breakdown in the combustion engine, we will find people are talking about this. Some people consider it as one part. It is the mechanical noise, because actually mechanical parts are correlated to each other. They are connected to each other. They are linked. a gear connected to another gear, which is connected to the belt and bearing, etc. So, because they are correlated, some people say this is the mechanical noise aggregately like this.
Yeah, I think that was my question. I mean,
Yeah. Some people also.
no.
Some people.
I mean, there is a problem, but which can create a lot of sources.
Yeah.
And for me, I think that what I meant is that sometimes the number of sources can be really, really large. And for example, on the last data set that you showed, you said that there was 8 sources.
Yes.
That in some kind of motor like that, I imagine that there is like a really large number of sources. Do you know what I mean?
Let me first distinguish very important property before my technique and all the techniques in the literature that I built on, which is the coherence technique. They suggest first that the sources are incoherent. They are intercorrelated. If the sources themselves, like the mechanical noise, are intercorrelated, I don't know, it will be very hard to find which is coming from which, because they are built on yeah, exactly. But the main assumption is that these sources that we want to separate or extract are incoherent, decorrelated between each other, like the combustion noise and the mechanical noise. The combustion noise doesn't have something to do with the mechanical noise. They're coming from a different physical phenomenon. So for sure they are decorrelated. But the mechanical noise, they are mainly correlated, even if they are coming from different parts. Okay? There is in the literature, in very old paper in the early 2000, there's some papers that say something about this mechanical noise that can be divided into type of noises, and I don't remember the name of this type of noises, but there is a huge research on this side. Okay, and the problem becomes more and more difficult when you don't know the physical nature of your machine. In the combustion engine, we know a lot about the nature of the physical phenomenon. But in the case of electrical machines and hybrid machines, it becomes more difficult to say. There is the magnetic noise. There is many type of noise. Needs a huge physical, investigations of decades to get familiar with and say that we can attribute this. For example, I can't say now that these 8 or 9 sources are coming from what physical phenomenon. I don't know. Okay, but maybe after 10 years.
Yeah. You mentioned that there's been a lot more research, obviously, on combustion engines.
Yeah.
Mainly mechanical noise and combustion. I'd assume an electric motor doesn't have combustion in it. Otherwise, there would be a big problem, I think.
No, there is no combustion.
And so I'm wondering, and it comes a bit out of the field of this study, but I'm wondering which are the main noise sources on an electric motor. I'd assume there would be like mechanical noise, but otherwise, is it like the magnets, or like how does it work? Where's the sound coming from? Mainly.
Yeah, I didn't read a lot about it, but from what I read, I know that there is different type of machines, electrical machines, electrical motors, and in some of them, which is a big part of the industry, big part of the market, or I don't know if it is called induction motor, something like that, I'm not sure. But in this type of motors, the magnetic noise is the major part of the noise.
Yeah, like in the car, you'd hear from like the.
Yeah, you can continue.
No, I meant the sound that comes from an electric car when it accelerates, the magnetic noise. It's like it makes a
exactly
noise.
And that's what I'm saying. That they found in some big group of the electric motors that the magnetic noise is contributing the most to the total noise of the machine.
I think what you are referring to is how do you say that, the switches inside the router. So it's just yeah, so it's organic at a defined frequency, so it's super high or 10K. So that's
Yeah, in order to have the circular motion.
It's basically from DC to AC.
Yeah.
I also have a question. So, because your approach is supervised source separation, I guess the several rate sources, they are incoherent, but they are different than the products of the principal component analysis, I guess, right? Because it depends on the references. So
let me clarify this. We have here in the first graph here on the left, up left. This is the principal components of the array, okay? And we have another set, which we're trying to use them to supervise the separation, if you can say. This is the reference set, and this is the eigenspectra of the reference, okay? And here is the eigenspectra of a very special linear combination of the reference set. What made this special is that we tried to get a linear combinations of the signals, not from linear combination directly from the eigenvalues, linear combinations of the reference signals that are maximally correlated to the signals of the array that we want, our target. Okay, so in this manner, we can say an optimal reference set, which is virtual. The reference set itself is a linear combination of the measured ones. Okay, and this is not a problem because actually the measured ones, in the overdetermined sense, when they use more references than the sources, so the measured ones actually is nothing but a linear combinations of the sources themselves. So we're doing a linear combinations of some linear combinations of what we want to try to estimate. So it's not a problem at all.
But from this specific example here, we can actually tell your maximally coherent spectrum is really similar to the eigenspectra of your data, right? Because in your references, it has like 2 eigenvalues.
Yes, it's more.
So in this case, it's more similar to principal component
Of
analysis.
that, exactly. Yeah. What made this looks like this? I think because we have in this reference set we have 3 microphones and 2 accelerometers. This difference in the SNRs, different types of different variances of the noise that caused these misguiding results.
I mean, it would be interesting to like have a comparison. Like, what if you only do blind source separation? Comes back to the form results.
Yeah.
What is interesting here is that we have a very, very nice data acquisition system because dynamic is more than 2,000 dBs.
Yeah.
More than excellent.
I tried to tune the experiment by making I tried to make it as clear as possible by getting the references as more as possible close to the source and making the array itself very far from the source.
Yes, I get it.
Yeah, this configuration is very important. We want to get the worst signals on the array and the best signals on the references, because that's what makes them references. Okay, and in this configuration we could get something very ideal. At some times, at some other experiments, at some instance, I got to only 1 eigenvalues, even using truncated SVD. Okay.
Don't you think you get picked up there because if your reference is so close to the loudspeaker.
I also had this problem because of the physics of the propagation of the sound in the air. Because when I get them very clear, I got some point there is no signal. You know these interactions. So I had to get them a little bit far, but not so far. And I tried until I get the signals, all the signals with constant power.
Okay,
It
thank
was
you
a hard
very
time.
much, Mohammed.
You're welcome. Thank you very much.
Presentation for